Imagine standing outside on a clear night, looking up at the sky. You see the moon, maybe a few bright planets, thousands of stars scattered across the darkness. It feels complete, doesn't it? Like everything worth knowing about our cosmic neighborhood is right there, visible and accounted for. We've mapped the planets, charted their orbits, sent probes to their moons. We've built a mental picture of the solar system that feels solid and final, a diagram we learned in school and never questioned again. But what if I told you that picture is incomplete? That somewhere out there, far beyond the reach of even our most powerful telescopes, there may be an entire world we've never seen. Not a moon, not an asteroid, but a planet, a massive, wandering giant, hidden in the deepest shadows of our solar system, orbiting so far from the sun that completing a single revolution around it takes longer than the entirety of recorded human history. This isn't science fiction. This is the story of Planet 9, a hypothetical world that exists at the very edge of scientific knowledge, somewhere between mathematical certainty and observational mystery. It's a world that, if it exists, would fundamentally change our understanding of where we live. And the hunt for it reveals something profound about how science actually works, about how we know what we know when we can't see it with our own eyes. The object in question would be enormous, at least twice the size of Earth, possibly 6 times more massive. Picture a sphere of frozen rock and ice, larger than anything in the outer solar system except the gas giants themselves. But unlike Jupiter or Saturn, this world would have no glowing atmosphere, no visible storms, no moons to give away its position. It would be dark, cold, nearly invisible, a ghost planet, and its orbit would be unlike anything else we know. While the other planets circle the sun in relatively neat, predictable paths along roughly the same plane, Planet 9 would trace a wildly elongated ellipse tilted 16 degrees off that familiar orbital disk. At its farthest point, it would swing out to a distance 500 times greater than the gap between Earth and the Sunday. Out there, the sun itself would shrink to just another bright star in the sky. Light from our star would take hours to reach this frozen world, and warmth would be a memory from some ancient, closer past billions of years ago. One orbit would take between 10,000 and 15,000 years. Think about that for a moment. The last time this planet, if it exists, completed a full circuit around the sun, humans were still living in caves, painting on stone walls, just beginning to plant the first crops. Civilizations have risen and fallen. Entire epochs of human history have passed, and Planet 9 would still be making its slow, lonely journey through the dark. But here's the strange part. Despite never having seen it, despite having no photograph or direct measurement of any kind, scientists are increasingly confident that something like this must be out there. Not because they want it to be true, not because it would be exciting or convenient, but because the math demands it. Because the outer solar system is behaving in ways that don't make sense unless something massive and unseen is pulling on it from the shadows. This is where the story gets truly interesting, because it forces us to confront a fundamental question about knowledge itself. How do you know something exists when you can't see it? How do you prove the presence of a world that may be invisible to every instrument we currently possess? The answer lies in one of the most powerful tools humans have ever developed, a method that has revealed more about the universe than any telescope ever could. The ability to read the invisible through its effects on the visible. We like to think we've solved the solar system, that we know every significant object circling our star. After all, we've been studying the planets for centuries. We've sent spacecraft to every major world, landed rovers on Mars, dropped probes into the clouds of Jupiter, watched storms rage on Saturn. The solar system feels known, cataloged, understood. But that confidence is an illusion born from proximity. We know what's close to us because it's bright and easy to see. The farther out you go, the darker and stranger everything becomes. The story of how we hunt for invisible planets begins not with modern technology, but with a discovery made over 2 centuries ago by a man who wasn't even looking for planets at all. In the spring of 1781, a musician and amateur astronomer named William Herschel was scanning the night sky from his backyard in England using a telescope he'd built himself. He was searching for comets, those icy wanderers that occasionally sweep through the inner solar system. On the night of March 13th, he noticed something odd, a faint, disk-like object that didn't look quite like a star. He assumed it was a comet and noted its position. But as he and other astronomers continued to observe this object over the following weeks, something became clear. It wasn't moving like a comet. It was moving in a slow, steady arc, far beyond the orbit of Saturn. This wasn't a visitor from the outer dark. It was a permanent resident, a seventh planet, orbiting peacefully where no planet was supposed to be. Herschel had stumbled onto Uranus entirely by accident, doubling the known size of the solar system in a single observation. It was the first planet discovered in recorded history, and it changed everything. But Uranus itself was about to reveal something even stranger. As astronomers tracked its orbit over the decades that followed, they noticed something wrong. The planet wasn't moving the way it should. According to the laws of gravity laid down by Isaac Newton a century earlier, Uranus should follow a smooth, predictable ellipse around the Sun, influenced only by the gravitational pull of the Sun itself and the other known planets. But Uranus was misbehaving. At certain points in its orbit, it would speed up. At other points, it would slow down, as if something unseen was tugging on it, pulling it slightly off course. This behavior has a name in astronomy. It's called a perturbation. Objects in space don't just do strange things on their own. If something is deviating from its predicted path, there's a reason. Some force, some mass, some gravitational influence must be acting on it. And if you can measure that deviation carefully enough, you can work backwards. You can use mathematics to reverse engineer the cause, to calculate the size and position of whatever invisible force is responsible. By the middle of the 19th century, two brilliant mathematicians, working independently on opposite sides of Europe, decided to do exactly that. Urbain Le Verrier in France and John Couch Adams in England both analyzed the strange wobbles in Uranus's orbit and came to the same conclusion. There had to be another planet out there, one that hadn't been discovered yet, one whose gravity was powerful enough to perturb Uranus in exactly the way they were observing. And using nothing but pen, paper, and Newton's equations, they calculated where that planet must be. In September of 1846, a German astronomer named Johann Galle received a letter from Le Verrier. The letter contained precise coordinates, a specific patch of sky where the mathematics predicted an undiscovered planet should be located. Galle pointed his telescope at that exact spot. Within hours, he found it, a pale blue disk, steady and bright, right where the equations said it would be. Neptune, the eighth planet, revealed not by accident, not by luck, but by pure mathematical prediction. It was one of the greatest triumphs in the history of science, proof that the universe could be understood, that its hidden structures could be decoded through reason and calculation. And naturally, scientists wanted to do it again. If math could find Neptune, maybe it could find something even farther out. So they turned their attention to Neptune itself, watching its orbit for any signs of perturbation, any hint that something beyond it was pulling on it the way Neptune had pulled on Uranus. And sure enough, they thought they found one. Neptune's orbit seemed to have a slight wobble. The hunt was on for a ninth planet. In 1930, after years of painstaking searches, an astronomer named Clyde Tombaugh discovered a faint, moving point of light in the constellation Taurus. It was named Pluto, and for 76 years it was celebrated as the ninth planet from the Sunday mission accomplished. The mystery solved. Except it wasn't solved at all, because Pluto was nowhere near massive enough to perturb Neptune. It was too small, too light, barely larger than Earth's moon. The supposed wobble in Neptune's orbit turned out to be a measurement error. Pluto was a real object, but it wasn't the planet they thought they'd found. This is where we encounter something crucial, something that runs through the entire history of planetary discovery. It's called observational bias. You go looking for something specific, and when you find anything at all in the general area where you expected it, you assume it must be what you were looking for. You fit the evidence to the theory instead of testing the theory against the evidence. Pluto appeared bright and large through the telescopes of the time because it's covered in reflective ice. But brightness doesn't mean mass. And without mass, Pluto couldn't be responsible for what astronomers thought they were seeing. So the hunt continued. But for decades, it went nowhere. The outer solar system remained a mystery, too distant and too dark to reveal its secrets easily. Then, starting in the 1990s, something remarkable happened. New telescopes, new digital imaging techniques, and new sky surveys began to uncover a hidden population of objects far beyond Neptune. Hundreds, then thousands of icy bodies, drifting in a vast ring around the outer edge of the planetary system. This region became known as the Kuiper Belt, and Pluto, it turned out, was just one member of this enormous population. Not a misfit planet, but the first discovered citizen of an entirely new category of solar system objects. The Kuiper Belt is strange and vast. Estimates suggest there are thousands of Pluto-sized objects out there, most still undiscovered. And beyond them, in the even colder reaches, there may be 100 billion smaller bodies, chunks of rock and ice, at least a kilometer across. Remnants from the formation of the solar system, drifting in slow, frozen orbits that take centuries to complete. It's a graveyard of planetary formation, a place where there wasn't quite enough material to build another world. So everything just stayed scattered and small. But here's where the story takes another turn. Because as astronomers cataloged more and more of these distant objects, they started noticing something deeply strange about how they were distributed. Most objects in the Kuiper Belt orbit more or less in the same plane as the planets, following roughly circular paths around the Sun. But a handful of them, the most distant ones, the ones that swing out farthest from the Sun, were behaving differently. Their orbits were elongated, tilted, clustered together in a way that seemed too organized to be random. It looked, to put it simply, like something had been shepherding them, nudging them into alignment over billions of years. In 2016, two astronomers at the California Institute of Technology, Mike Brown and Konstantin Batygin, published a paper that sent shockwaves through the planetary science community. They had analyzed the orbits of a small group of these extreme Kuiper Belt objects and found a pattern. These objects were all orbiting in the same direction, tilted at similar angles, grouped together in space in a way that defied probability. If their orbits were random, the chance of this clustering happening by accident would be vanishingly small. Brown and Batygin proposed a solution. What if there was a ninth planet out there, far beyond the Kuiper Belt, massive enough to gravitationally herd these distant objects into their current configuration? They ran computer simulations, modeling the solar system as it would have looked billions of years ago, when the planets were newly formed and the Kuiper Belt was still settling into place. They ran the simulation twice, once with a large, unseen planet in the outer system, once without. The version without the planet produced random, scattered orbits. The version with the planet produced exactly the clustering pattern observed in the real sky. The fit was so precise, the correlation so strong, that the researchers calculated a 99.6% probability that something like Planet 9 must exist. Not proof, not yet, but a compelling mathematical argument that something massive and invisible is shaping the outer solar system in ways we can see but not yet explain. So we're left with a profound question. If the evidence is this strong, if the math points so clearly toward the existence of a massive, hidden world, why haven't we found it yet? And perhaps more intriguingly, how did such a planet end up out there in the first place, stranded so far from the Sun that it takes millennia to complete a single orbit? The first question is easier to answer than you might think. Finding Planet 9, if it exists, would be an extraordinarily difficult task, far harder than the discovery of Neptune. When Johann Gall pointed his telescope at the coordinates provided by Leverrier, he was looking for an object that, while distant, was still close enough to reflect a meaningful amount of sunlight. Neptune is bright. It has a thick atmosphere of hydrogen and helium that scatters light efficiently. Even at its distance, it's visible through a reasonably powerful telescope if you know where to look. Planet 9 would be nothing like that. The hypothetical world would sit 15 times farther from the Sun than Neptune, possibly more. At that distance, sunlight becomes almost meaningless. The Sun itself would appear as little more than an especially bright star, offering virtually no heat and precious little illumination. Any light that does reach Planet 9 would have to travel all the way back to Earth to be detected. And by then, it would be so faint that only the most sensitive instruments on the planet could hope to pick it up. And unlike Neptune, Planet 9 wouldn't have a bright, reflective atmosphere. It would be a dark, frozen core of rock and ice, the kind of object that absorbs light rather than reflecting it. Imagine trying to spot a charcoal briquette floating in the darkness, miles away, illuminated only by a distant candle. That's the scale of the challenge. Even with the best telescopes currently in operation, Planet 9 would be incredibly dim. a faint smudge of light that could easily be mistaken for a distant star or a cosmic ray artifact on a camera sensor. There's also the problem of knowing where to look. Neptune was found quickly because the math pinpointed its location with remarkable precision. But Planet 9's orbit is so elongated, so tilted, that the possible positions it could occupy span a huge swath of the sky. Astronomers have narrowed it down somewhat, but they're still talking about searching thousands of square degrees. That's not a needle in a haystack. That's a needle in a field of haystacks, and you're not even sure which field. The search is made harder still by the fact that the sky is constantly changing. Distant stars, galaxies, and other objects move across our field of view as Earth rotates and orbits the Sunday Dallas. To identify a planet, you need to find something that moves in a way consistent with an object in our solar system. Something that shifts position slowly over weeks or months. That requires multiple observations of the same patch of sky, careful comparisons, and the patience to rule out false positives. It's painstaking work, and it's entirely possible that Planet 9 has already appeared in images captured by surveys over the past decade, sitting unnoticed in the data, waiting for someone to recognize what they're looking at. But assuming Planet 9 is real, there's a second mystery that's arguably even more fascinating than the search itself. How did it get there? Planets form from the disk of gas and dust that surrounds a young star. In our solar system, that disk was densest close to the Sun, where heat and gravity work together to clump material into larger and larger bodies. The inner planets, Mercury, Venus, Earth, Mars, formed from rock and metal, materials that could survive the heat. Farther out, beyond what's called the frost line, temperatures dropped low enough for water and other volatile compounds to freeze, allowing the gas giants to accumulate enormous atmospheres of hydrogen and helium. The Kuiper Belt exists because it's the region where the disk ran out of material. There simply wasn't enough density out there to build a full planet, so everything remained small and scattered. This means that Planet 9, if it's as massive as the models suggest, couldn't have formed where it is now. There wasn't enough material that far out to build something 6 times the mass of Earth. It had to come from somewhere else. One possibility is that Planet 9 formed much closer to the Sun, somewhere in the region between Saturn and Neptune, during the chaotic early days of the solar system. In that scenario, the young planet began to accumulate mass, pulling in gas and ice on its way to becoming another gas giant. But before it could finish growing, something went wrong. A close gravitational encounter with one of the other forming giants, Jupiter, Saturn, Uranus, or Neptune, could have flung it outward, ejecting it from the inner system with enough force to send it careening toward the outer dark. It wouldn't have been kicked hard enough to escape the Sun's gravity entirely, but it would have been sent into a highly elongated orbit, far beyond the orbits of the other planets. Over billions of years, gravitational interactions with the remaining planets and the scattered debris of the outer system would have gradually smoothed out some of the chaos, settling Planet 9 into the long, tilted orbit that the models predict. In this version of events, Planet 9 is a failed gas giant, a planetary core that never got the chance to finish what it started, exiled to the frozen edge of the solar system before it could grow into something like Jupiter or Saturn. But there's another possibility, one that's even stranger. What if Planet 9 didn't form in our solar system at all? What if it's a rogue planet, a world that was born around a completely different star, ejected from its home system, and captured by our Sun billions of years ago? Rogue planets are not hypothetical. We know they exist. When planetary systems form, they're chaotic and violent places. Young planets migrate, collide, and gravitationally scatter each other. Some get flung out of their home systems entirely, cast into interstellar space to wander the galaxy alone. These rogue worlds drift through the darkness between stars, unbound to any sun, invisible except for the faint heat they still radiate from their formation. Current estimates suggest there may be billions of rogue planets in our galaxy, vastly outnumbering the stars themselves. If one of these wanderers passed close enough to our solar system during its early history, the Sun's gravity could have captured it, pulling it into a bound orbit. The mechanics of such a capture are tricky. Getting the timing and trajectory just right requires specific conditions, but it's not impossible. If this is what happened, then Planet 9 would be an immigrant, a world that spent its youth circling a different star, only to be adopted by ours after an encounter in the dark. In either case, whether it's a failed gas giant or a captured rogue, Planet 9 would be an incredibly hostile place. Temperatures out there would hover just a few dozen degrees above absolute zero. No atmosphere could survive in that cold. Any gases would have long since frozen and fallen to the surface as ice. The surface itself would be a lifeless expanse of frozen volatiles, water ice, methane ice, ammonia ice, coating a core of rock and metal. There would be no weather, no seasons, no change of any kind. Just an eternal, frozen twilight, broken only by the faint, distant glow of the Sunday. If you were somehow able to stand on the surface of Planet 9 looking up, you wouldn't see the solar system you recognize. The sun would be a bright star, brighter than any other, but no longer the blinding disk that dominates our sky. Earth, Mars, Jupiter, none of them would be visible to the naked eye. You would be utterly alone at the edge of a planetary system that extends far beyond what most people imagine when they picture the solar system. But here's the thing. Despite all the evidence, despite the simulations and the mathematical certainty, Planet 9 remains hypothetical. It hasn't been seen. It hasn't been photographed. And in science, seeing is believing, or at least it's the final step in the process. Until someone points a telescope at a specific patch of sky and finds a moving object that fits the predicted characteristics, Planet 9 will remain a compelling idea rather than a confirmed fact. And that brings us back to the question of observational bias. Brown and Badigan went looking for evidence of a large, distant planet. They found orbital anomalies that seemed to fit the profile. But could there be other explanations? Are we making the same mistake astronomers made with Pluto, assuming that the first thing we find must be what we're looking for? Some researchers think so. One alternative explanation is genuinely wild. What if, instead of a planet, there's a primordial black hole drifting through the outer solar system? These objects are purely theoretical, proposed to have formed in the first moments after the Big Bang, when the universe was still a hot, dense soup of matter and energy. In regions where density was especially high, matter could have collapsed directly into black holes, skipping the usual process of star formation entirely. These primordial black holes would be tiny, some no larger than a marble, but incredibly massive, with enough gravitational pull to warp space-time around them. If one of these objects happened to be wandering through our solar system, its gravity could, in theory, produce the same kinds of orbital perturbations attributed to Planet 9. It would be almost impossible to detect directly, since black holes don't emit light, but its gravitational effects would be unmistakable. The idea is fascinating, but most astronomers consider it unlikely. Primordial black holes, if they exist at all, are thought to be extraordinarily rare. The chances of one passing through our solar system and then being gravitationally captured by the sun are vanishingly small. It's not impossible, but it requires stacking unlikely event on top of unlikely event. Occam's razor suggests that a planet, something we know can exist and form naturally, is a simpler and more probable explanation. Another alternative is more mundane but no less interesting. What if gravity itself behaves differently at extreme distances from the sun? All of our predictions about orbits and gravitational interactions are based on laws formulated by Isaac Newton in the 17th century and refined by Albert Einstein in the 20th. These laws have been tested extensively in the inner solar system and have proven remarkably accurate. But Newton and Einstein never had data from objects orbiting 500 times farther from the sun than Earth does. It's possible, though speculative, that gravity doesn't scale in exactly the way we think it does at such vast distances. Perhaps there's some small correction factor, some subtle modification to the equations, that only becomes noticeable when you're dealing with orbits that take tens of thousands of years to complete. If that's the case, then the strange clustering of Kuiper Belt objects might not require a ninth planet at all. It could simply be a natural consequence of how gravity works in the deep outer system. A detail we've missed because we've never had reason to look for it before. If you're enjoying this journey into the nature of reality, consider subscribing to our channel, Broken Zach, so you don't miss what comes next. This is one of the beautiful, frustrating aspects of science. It's never quite finished. Every answer raises new questions. Every discovery reveals how much we still don't understand. We like to think we've solved the solar system because we can see the planets, because we've sent probes to their moons, because the orbits look predictable and neat in our diagrams. But the more carefully we look, especially at the distant, dark edges of the system, the more we realize how much is still hidden from us. The truth is, We've only explored a tiny fraction of the space that falls under the Sun's gravitational influence. The Kuiper Belt extends out to about 50 astronomical units from the Sun, 50 times the distance from the Earth to the Sunday. But the Sun's gravity doesn't stop there. Far beyond the Kuiper Belt lies another region, even more distant and mysterious, called the Oort cloud. This is a vast, spherical shell of icy objects, stretching out to nearly a light year from the Sun, halfway to the nearest star. It's the source of long-period comets, the ones that take centuries or millennia to complete a single orbit. We've never directly observed the Oort cloud. It's too far away, too faint, too diffuse. We know it's there because comets occasionally fall inward from that region, their orbits perturbed by passing stars or gravitational tides from the galaxy itself. But we have no detailed map of it, no census of its objects, no clear understanding of its structure. It's possible that Planet 9, if it exists, is not the only large object lurking out there. There could be others, smaller or more distant, waiting to be discovered. This is the frontier of planetary science. Not the bright, warm worlds close to the Sun, but the cold, dark places at the edge of the light, where our knowledge fades into uncertainty and speculation. And soon, we may finally have the tools to pierce that darkness and see what's really out there. In the summer of 2025, a new telescope began operations at the Vera Rubin Observatory in Chile. It's not just any telescope. It's one of the most advanced instruments ever built for astronomy, equipped with the largest digital camera in the world, a device capable of capturing images with a resolution so high that you could spot a golf ball from 15 miles away. The camera weighs 3 tons, has a field of view 7 times wider than the full moon, and can capture the entire visible night sky, from horizon to horizon, once every 3 nights. The Vera Rubin Observatory isn't designed to search for any one specific object. Its mission is broader and more ambitious. For the next 10 years, it will scan the night sky continuously, taking millions of images, creating a vast time-lapse record of everything visible from its location. Every asteroid, every comet, every distant galaxy, every object that moves or changes will be cataloged and tracked. The data will be processed by powerful computers, algorithms, sifting through the flood of images to identify anything unusual, anything that doesn't fit the known catalog of objects. And that's how Planet 9, if it exists, will likely be found. Not through a targeted search, but through this kind of systematic, exhaustive survey. Somewhere in that time-lapse, if there's a massive, dark object drifting slowly through the outer solar system, it will reveal itself. Its motion, tiny but detectable, will stand out against the background of distant stars. The algorithms will flag it. Astronomers will follow up with additional observations, refining its orbit, confirming its nature. If Planet 9 is real, we'll know within the next decade. And if it's not, if the surveys come up empty, then we'll need to rethink the evidence, reconsider the explanations, and confront the possibility that the outer solar system is even stranger than we imagined. But let's step back for a moment and consider what all of this really means. The hunt for Planet 9 is not just a story about finding a missing world at the edge of the solar system. It's a story about the nature of knowledge itself, about the kinds of evidence we accept, and about the tension between what we can see and what we can infer. For most of human history, seeing was the only way of knowing. If you couldn't observe something directly with your own senses, it didn't exist in any meaningful way. The sky was a dome of lights, the earth was flat and motionless, and everything beyond the horizon was speculation. But then we developed tools, telescopes, microscopes, instruments that extended our senses beyond their natural limits. And more importantly, we developed mathematics, a language that allowed us to describe the invisible, to predict what should be there, even when we couldn't see it. The discovery of Neptune was a turning point. It proved that you could know something exists without seeing it first. You could deduce its presence from its effects, work backwards from the evidence to the cause, and use pure reasoning to pinpoint the location of an object no human eye had ever glimpsed. This was a profound shift in how we understand reality. It meant that the universe was not limited to what we could perceive. It meant that there were structures, forces, and objects operating beyond the reach of our senses, and yet we could still comprehend them, map them, predict them with astonishing precision. Planet 9 represents the next step in that process. If it's confirmed, It will be the first major solar system object discovered primarily through gravitational archaeology, through the careful analysis of how distant bodies move and cluster. It will be found not because someone spotted it through a telescope, but because the mathematics demanded it, because the patterns in the data could not be explained without invoking something large and unseen. And this raises a deeper question, one that extends far beyond astronomy. How much of reality operates this way? How much of what exists is fundamentally invisible to us, knowable only through its effects on the things we can observe? The answer, it turns out, is most of it. Consider the structure of matter. You cannot see an atom, even with the most powerful microscope. Atoms are far too small, smaller than the wavelength of visible light itself, and yet we know they exist. We know their structure, their behavior, the forces that bind them together. We know this because of the way materials behave, the patterns in chemical reactions, the spectral lines emitted by heated elements. We've built an entire understanding of atomic physics not by seeing atoms directly, but by observing their effects and working backwards to deduce what must be causing those effects. The same is true for much of fundamental physics. Electrons, quarks, neutrinos, these are not things you can see. They're inferred from tracks in particle detectors, from the energy balances in collisions, from the decay patterns of unstable particles. We've never seen a magnetic field or an electric field, yet we manipulate them constantly because we understand how they influence charged particles. We've never seen space-time curve, but we can measure the bending of light around massive objects, the precession of planetary orbits, the gravitational waves rippling out from colliding black holes. Even the most familiar aspects of reality turn out to be indirect. You think you see the world around you, but what you're actually seeing is reflected light, photons that bounced off objects and happen to hit the receptors in your eyes. Your brain constructs an image from that data, filling in gaps, making assumptions, creating a coherent picture from incomplete information. The redness of an apple, the hardness of a table, the warmth of sunlight on your skin. These are interpretations, models built by your nervous system to help you navigate a reality that is, at its core, far stranger and more abstract than your direct experience suggests. This is the philosophical heart of the Planet 9 story. It's a reminder that the universe doesn't care whether we can see it or not. It exists independently of our observations, operating according to laws that we can only grasp through patient, careful reasoning. And the more we learn, the more we realize that the visible universe is just the surface, a thin layer of light and matter floating on a vast ocean of invisible structure. But there's a risk here too, a danger that comes with relying too heavily on indirect evidence. It's easy to become overconfident, to mistake a compelling mathematical model for objective truth. The history of science is full of examples where elegant theories turned out to be wrong, where observations that seemed to demand a particular explanation were eventually explained by something entirely different. Vulcan, for instance. In the 19th century, astronomers noticed that Mercury's orbit didn't quite match the predictions of Newtonian gravity. The planet's perihelion, the point in its orbit closest to the Sun, was precessing slightly faster than it should. This looked exactly like the kind of perturbation that had led to the discovery of Neptune. So astronomers proposed the existence of Vulcan, a small planet orbiting even closer to the Sun than Mercury, whose gravity was responsible for the anomaly. They searched for Vulcan for decades. Some even claimed to have seen it, but Vulcan didn't exist. The real explanation turned out to be far more profound. Mercury's orbit was being influenced not by an unseen planet, but by the curvature of space-time itself, an effect predicted by Einstein's general theory of relativity. Newtonian gravity, it turned out, wasn't quite right. It was an approximation that worked well most of the time, but broke down in strong gravitational fields. The anomaly wasn't evidence for a new planet, it was evidence for a new theory of gravity. Could Planet 9 be another Vulcan? Could the orbital clustering in the Kuiper Belt be explained by something other than a massive, distant planet? It's possible. The difference is that this time, we have the tools to settle the question definitively. The Vera Rubin Observatory and other next-generation surveys will map the outer solar system with unprecedented detail. If Planet 9 is there, it will be found. If it's not, we'll know that too. And we'll have to come up with a better explanation for the patterns we're seeing. But regardless of what we find, the process itself is valuable. The act of searching, of testing predictions against observations, of refining models and ruling out alternatives, this is how science works. It's messy, uncertain, and often frustrating. It doesn't give us instant answers or absolute truths, but it does give us something arguably more important, a method for interrogating reality, for separating what we think we know from what we actually know, for moving step by step closer to an accurate understanding of the universe. And that brings us to you, to the person watching this, sitting somewhere on a planet that orbits a star at a comfortable distance, looking up at a sky that seems familiar and comprehensible. What does any of this mean for your everyday life? Why should you care whether there's a ninth planet lurking in the outer dark? The answer is that the questions we're asking about Planet 9 are the same questions we should be asking about everything. How do I know what I know? What evidence am I basing my beliefs on? Am I seeing reality directly? Or am I seeing a model, an interpretation, a simplified version constructed by my limited senses and cognitive biases? Most people go through life assuming that their perception of the world is accurate, that what they see is what's really there. But the story of Planet 9, and really the entire history of science, suggests otherwise. The universe is far larger, stranger, and more complex than it appears. Most of what exists is invisible. Most of the forces shaping your life operate below the threshold of direct perception. Your own thoughts and experiences are mediated by a brain that constructs reality from incomplete data, filling in gaps, making guesses, presenting you with a simplified interface that's useful for survival but not necessarily true in any absolute sense. This doesn't mean reality is unknowable. It means that knowing reality requires effort, skepticism, and a willingness to question your own assumptions. It means accepting that the obvious answer isn't always the right one, that sometimes the truth is hiding just out of sight, waiting to be revealed through careful observation and rigorous reasoning. The outer solar system is a perfect metaphor for this. It's a place where sunlight fades to almost nothing, where the familiar planets give way to icy debris and vast, empty distances. It's a place where our intuitions fail, where we can't rely on what we see because there's almost nothing to see. And yet, even there, we can find truth. We can map the invisible, track the unseen, and piece together a picture of reality that extends far beyond the reach of our eyes. If Planet 9 exists, it will be one of the most significant discoveries in modern astronomy. It will reshape our understanding of how the solar system formed, how planets migrate and interact, and what kinds of worlds can exist at the frozen edge of a star's gravitational influence. It will be a reminder that even after centuries of exploration and study, our cosmic neighborhood still holds surprises. But even if Planet 9 doesn't exist, even if the search comes up empty and we have to rethink the evidence, that will be valuable too. It will mean we've learned something important about the limits of our current models, about the dangers of confirmation bias, about the need to remain skeptical even in the face of compelling mathematical arguments. It will mean we've tested a hypothesis rigorously and found it wanting, which is just as much a part of the scientific process as confirming a prediction. Science is not a collection of facts. It's a method, a process, a way of interrogating the world that prioritizes evidence over intuition, observation over assumption, and brutal honesty over comforting certainty. It's a way of thinking that acknowledges how easy it is to be wrong, how seductive it is to believe what we want to believe, and how important it is to test our ideas against reality until they either break or prove themselves sturdy enough to withstand scrutiny. The search for Planet 9 is still ongoing. Right now, as you're watching this, telescopes are scanning the sky, computers are processing data, and astronomers are analyzing orbits, looking for the telltale signs of a massive, hidden world. Within the next few years, we'll likely have an answer. Either we'll find it, capturing an image of a dark, frozen sphere at the edge of the solar system, or we'll rule it out, forcing ourselves to come up with a new explanation for the strange patterns we've been observing. But whatever we find, the real discovery has already been made. It's the realization that the universe is not limited to what we can see, that reality extends far beyond the reach of our senses, and that through careful observation, patient reasoning, and a willingness to follow the evidence wherever it leads, we can understand even the things that remain invisible. That's the true power of science. Not that it gives us all the answers, but that it gives us a way to find them. Not that it reveals reality all at once, but that it teaches us how to peel back the layers, one by one, exposing the hidden structures beneath. And not that it eliminates mystery, but that it shows us how to transform mystery into knowledge, ignorance into understanding, darkness into light. So the next time you look up at the night sky, remember this. The solar system you learned about in school, the neat diagram with 8 planets orbiting in orderly rows, is incomplete. There are worlds out there we haven't found yet, structures we haven't mapped, phenomena we don't fully understand. The darkness at the edge of the solar system is not empty. It's full of secrets, waiting for us to develop the tools and the courage to uncover them. Planet 9, if it exists, is just one of those secrets. But it represents something larger, the idea that no matter how much we've learned, no matter how far we've come, there's always more to discover. The universe is not a finished puzzle with all the pieces in place. It's an ongoing exploration, a story that we're still writing, a mystery that deepens the more carefully we examine it. And that, ultimately, is why this matters. Not because finding another planet would change your daily life in any practical way, but because it would remind you that you live in a cosmos far grander and stranger than you probably imagine. That there are wonders still hidden from view, truths waiting to be uncovered, and questions whose answers will reshape everything we think we know. The hunt for Planet 9 is a hunt for understanding. It's an attempt to push back the boundaries of ignorance, to see a little farther into the dark, to grasp a little more firmly the deep structures that govern the universe. And whether we find what we're looking for or not, the act of searching will have been worth it. Because in the end, that's what it means to be human. To wonder, to question, to refuse to accept the surface appearance of things, to insist that reality can be known, even when it hides itself from view, to believe that somewhere out there, in the cold and darkness at the edge of everything, there are truths waiting to be discovered, and to never stop looking. If you enjoyed this video, watch this one too. It's a great one, and we'll see you in the next video.